All right, welcome back. Last example in this section. This is a past exam question from an exam one. It involves the area between two curves, but it's a bit of a doozy, this one. There's a few extra unknowns thrown in that we have to sort of work backwards almost to figure out what's going on. So let's just read the question and try to understand what's happening. We've got parts of the graph of the functions f of x equals x cubed minus ax and g of x equals ax are shown in the diagram below. So y equals g of x, that's our linear function, and f of x is the cubic. The graphs intersect when x equals 0 and when x equals m, and that's kind of shown on our graph as well. We've got points of intersection at 0 and m. And then we're told that the area of this shaded region is 64. The question's asking us to find the values of a and m. Now, general rule of thumb, if you've got two unknowns that you need to solve for, you're probably going to have to set up two equations, or you're going to have two sort of separate bits of information to come together to have a solution for a and a solution for m. So, a couple of different places that we could start. Often with area between two curves questions, we start with points of intersection because they give us our terminals. So we can do that here. We can say, well, the point of intersection, that would obviously occur when f of x equals g of x. So in other words, when x cubed minus ax equals ax. So the intersection occurs at x cubed minus ax equals ax. But the question told us, and we can see it on the graph, that the functions intersect, well, yes, when x equals 0, but also when x equals m. So what we can actually do is sub in x equals m to this equation, and that will give us, so when x equals m, this becomes m cubed minus am equals am. Or, in other words, we could say that m cubed, if I subtract the am from the right-hand side, I get minus 2am equals 0. Now that equation on its own can't be solved for a and m, but it obviously is one equation that shows a relationship between a and m. If we can come up with another one, we can use simultaneous equations, and that's exactly what we have to do. So that's generating an equation from the intersection. The other information that we knew was the area of the shaded region, and so from the area, we can say, well, okay, this area would be given by the integral from 0 to m of function that's on top is g of x, okay, and that was ax, so ax goes first, minus the function on the bottom, which is f of x, and the rule for f of x is x cubed minus ax, so minus x cubed minus ax with respect to x. But we know from the question that that area is equal to 64 units, or 64 square units, I should say. So we can actually now, as far as we can go, we can evaluate this definite integral to come up with another equation involving a and m that we can use to solve for those two unknowns. Before we integrate, I'll just simplify this part here. So we've got an ax minus negative ax. Okay, so we've got two lots of ax minus x cubed with respect to x. All right, so at this step, let's anti-differentiate in terms of x. So 2ax will become 2ax squared over 2. Okay, so 2ax squared over 2 would actually just be ax squared. Minus x cubed, so that's going to become minus x to the power of 4 over 4. Terminals are 0 and m. That's all equal to 64. All right, so now our job is to sub in x equals m. So we get am squared minus m to the power of 4 over 4 minus sub in 0, and when we sub in x equals 0, both of these terms are just going to become zeros. So 0 minus 0 equals 64. And so that means am squared minus m to the power of 4 on 4 equals 0. So we now have two equations, one here, two different equations that involve a and m. We should be able to use simultaneous equations to solve for a and solve for m. A couple of possible approaches that we could use. One would be to try to use some substitution, so try to rearrange one of these equations to get a or m on its own, and then sub that into the other equation, and that's probably the best method, I think, here. So let's try taking equation 1, and let's try to get a on its own. So we could go m cubed equals 2am, divide both sides by 2m, and we can do that because we know that m is not equal to 0, and that would give us a equals m cubed over 2m, and therefore a equals m squared over 2. Okay, and that can now go into here, into equation 2, and therefore we can kind of make that substitution in place of a, so we get m squared onto times m squared minus m to the power of 4 on 4 is all equal to, oh, sorry, why did I do equals 0 before? That was silly of me. That should say equals 64. Equals 64. Sorry about that. Equals 64. Okay, so let's see if we can solve this equation for m, because this now only has m's in it. So m to the power of 4 on 2 minus m to the power of 4 on 4 equals 64. Look, a couple of approaches here. What we might do is actually just multiply everything by 4 to get 2m to the power of 4 minus m to the power of 4. And 64 times 4, well, if you double it, you get 128. You double it again, you get 256. And so we get m to the power of 4 equals 256, which means m would equal the fourth root of 256. And the fourth root of 256, ooh, what's that going to be? 8, I think, isn't it? 8 times 8 is 64. No, it's not going to be that. It's going to be 4, isn't it? 4 times 4 is 16. Times 4 again is 64. Times 4 again is 256. Yep. So the fourth root of 256 is 4. Got there in the end. Now, technically speaking, this is plus or minus 4. But we know from the picture, and from the picture, that we know that m is greater than 0. So m's not going to be plus or minus 4. It's equal to 4. Okay, now that we've got m, we can go back to here and say, well, okay, we knew that a was equal to m squared on 2. So this sort of back and forth, but from here, we can go back up to this equation and say that a will equal 4 squared on 2. So 16 on 2, which is 8. Right, and so a equals 8 and m equals 4, and we might just make that super clear that that's our final answer. I'm just going to write m equals 4 over here and make it stand out to whoever's marking my work that that's the final answer. So, very tricky one. I can't remember how many marks this question was worth. I imagine it would have been 3 or 4 because there's a lot of steps, but an indication of, particularly towards the end of exam 1, you will get questions that require quite a lot of manual working out. So it's worth practicing this. Obviously, we need to do some questions with the calculator, but certainly plenty of questions without the calculator as well to build up these kind of skills in questions that are pretty messy.